Introductory Chemistry, Chapter 10, Chemical Bonding, Lesson 1. So there's all types of different bonding theories. And remember, when we talk about theories, we're not talking about just stuff that people make up. These are things that have been proven. So you have valence bond theory, which looks at atomic orbital overlap. You have molecular orbital theory, which looks at how atomic orbitals can combine to form molecular orbitals. We're going to focus on Lewis theory, which looks at the valence electrons of particular atoms and how they can either be transferred or shared to form bonds. And the rule that governs whether or not we're going to lose, gain, or share electrons is the octet rule. So the octet rule states to have 8 valence electrons in your outermost shell that you are the most stable. So we play the game. We give, take, or share so that we can get to 8. Elements that will always follow the octet rule are carbon, nitrogen, oxygen, and fluorine. When they form covalent bonds, they will always have a total of 8 electrons, whether they be in lone pairs or bonded pairs. Atoms that will have less than, and the one that we most need to pay attention to is hydrogen. So when you draw hydrogen in a structure, it can only have one bond. No lone pairs of electrons, just one bond. Beryllium and boron will also have less than an octet, and helium will always have less than an octet as well. So an expanded octet means that you can have more than 8 electrons. This is going to happen for elements that are in row 3 or below if you are a non-metal or a semi-metal. And to have an expanded octet, you're only going to do this if you're the central atom, and you have to. Otherwise, all of those elements would just like to follow the octet rule. So what do I mean by this? Sulfur would like to have 8, but if it is bonding to more than a certain number of atoms, it can do that. It doesn't have to, but it will. And a chemical bond is just going to occur once we have either transferred our electrons, and then we end up with positive and negative charges, so we attract by electrostatic force, or we're sharing electrons. And we're mostly going to focus on sharing electrons in this chapter. So our Lewis-Dot symbols for representative elements. We look at our group number. Group 1 has 1, group 2 has 2, group 3 has 3, etc. So we count across. The only thing that's different is helium is a group 8, but it only has 2 electrons. It's not going to form any bonds anyway, so we can kind of just ignore that. So what are we focusing on here? We're focusing on the fact that your group number tells you your number of valence electrons. And when you show your electrons, they are simply dots. And what you want to do is you want to kind of go around like a clock and add your electrons, showing things unpaired before we pair them up. So then when we look at carbon's group, we look that it has 4 lonely electrons, which means it wants to make 4 bonds. Nitrogen has 3 lonely electrons. It would like to make 3 bonds. Oxygen has 2 lonely electrons, so it would like to make 2 bonds. And fluorine has 1 lonely electron, so it would like to make 1 bond. And the rest of the elements in the group will follow suit. So how do we write Lewis structures? So we draw our skeletal structure first. So we're going to identify our central atom, which typically there's just one of that particular atom. And most oftentimes it's the least electronegative. We will always draw 1 bond between all of the atoms that surround the central atom. So we have to make sure we count our total number of valence electrons to make sure that our structure makes sense when we're finished with it, going off of group numbers. Then we add electrons for negative charges and subtract electrons for positive charges. And so as we go along, we're going to bond our atoms and then put on lone pairs of electrons. So we put our pairs of electrons on all the terminal atoms first, and then the central atom. If the central atom has fewer than 8 electrons, you have to move 1 or more pairs from the surrounding atoms to make multiple bonds. But this is your last step. You only do this if you absolutely have to. So it's draw your central atom, draw single lines connecting all the other atoms, put dots on everything so that everything has 8 except for hydrogen. Then go back and compare how many electrons do I have in my structure versus how many do I have from my valence electron count. You then erase pairs of electrons if need be. Typically, when you erase those dots, it's going to mean that you're going to have to form a double bond or a triple bond somewhere. So NF3, nitrogen trifluoride. So I put nitrogen in the middle, I surround it by fluorine, I do an electron count. Nitrogen brings 5, there's 1 of them. Fluorine brings 7, there's 3 of them. So 5 plus 3 times 7 tells me I have 26 valence electrons. So then I'm going to draw my single bonds between my central atom and my surrounding atoms and then add dots to everything. I then do an electron count to show there's 2, 4, 6, 8 for fluorine, 2, 4, 6, 8 for this fluorine, 2, 4, 6, 8 for this fluorine. Nitrogen has 2, 4, 6, 8, so we're good. Everything has its 8, and then we count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, matches the 26 here, and this shows us what our structure is. So how about for the carbonate ion? So carbon is less electronegative than oxygen. We put it in the center. Carbonate is CO3 with a -2 charge. So carbon is group 4 valence electrons. Oxygen is group 6 valence electrons. We multiply by 3. And then a -2 charge means we add in an extra 2 electrons. So this structure has to have 24 valence electrons. So we go in by drawing single bonds and then giving everything its octet, putting on all of our electrons. So we look, we do a count, 2, 4, 6, 8, we're good, 2, 4, 6, 8, we're good, 2, 4, 6, 8, we're good, 2, 4, 6, 8, we're good. And then we count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have too many electrons, which means that we're going to have to erase a pair of electrons. If we erase a pair of electrons, then that means that we are going to have to double bond something. So we go in, we take a pair of electrons away, and we end up drawing a double bond from the carbon to another oxygen. So what else can we do? Carbon dioxide is going to show that we have carbon double bonded to each oxygen. We put carbon in the middle. We know it brings 4. Each oxygen brings 6. So that's a total of 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. So we're showing here that carbon has its 8 electrons. Oxygen also has its 8 electrons. We can always replace our bonded pairs that we're showing between atoms with lines, and I think it just makes the structure look a little bit easier to deal with. So carbon double bonds to both oxygens to have a stable structure. How about a triple bonded molecule like nitrogen? So nitrogen ends up sharing 3 pairs of electrons so that each nitrogen has 8. And we can represent our triple bond by 3 lines connecting the nitrogen atoms. So we show here we've got a total of 8 electrons for this nitrogen. We have 8 electrons for the other nitrogen, and we are forming a triple bond. Some exceptions to the octet, when we have an incomplete octet, like beryllium hydride, when beryllium brings 2, each hydrogen brings 2, we can only have a total of 4 electrons. So we're simply bonding beryllium single bonds to each hydrogen. Boron trifluoride, boron brings 3, fluorine brings 7. There are 3 of them, so 21 plus 3 is 24 electrons. And we see that boron has made single bonds to each of the fluorine atoms, noting that there are 8 for each fluorine, but only 6 for boron. Some other exceptions to the octet would be when we have odd electron molecules, or something that we call a radical. Nitrogen brings 5, oxygen brings 6. So we have an instance here where not each element gets its 8 electrons. Oxygen is going to get its 8 before nitrogen because oxygen is more electronegative, so it's going to pull the electron towards it. And then we can see that we're forming a double bond. So nitrogen only ends up with 7 electrons, while oxygen ends up with 8. We do our count: 2, 4, 6, 8, 10, 11, 11 electrons, 11 electrons. So an expanded octet would be something like sulfur hexafluoride. Sulfur brings 6 electrons. Each fluorine brings 7, so 7 times 6 is 42. I add that up, we get 48 total electrons. I put sulfur in the middle. I single bond each of my fluorine atoms. I see that each fluorine has 8 electrons, which it needs to have. And then I've got 8 times 6, which matches 48, so that's good. Sulfur has 2, 4, 6, 8, 10, 12 electrons, but it is allowed to do that because it is row 3 or below. And it has those electron pockets that it can put extra electrons in if it needs to, right? The pocket exists in your pants whether you have anything in it. So elements that are row 3 and below have electron pockets that allows them to make more bonds when necessary.